So this talk is about integrable sigma models and RG flow. So I want to be kind of fairly pedagogical about some things, since this is a journal club. And let me start off by talking about sigma models. So this is this class of 1 plus 1D scalar field theory on flat Minkowski space. So the scalar fields are x mu here. So mu is just a flavor index for the scalars. And this model is specified by a choice of this matrix G plus B, which we conventionally split into this symmetric part G and an anti-symmetric part B. And so of course, in the string theory context, G and B have a really kind of physical interpretation as physical fluctuating fields. And for us, they're actually just, from the point of view of this sigma model, they're just kind of frozen backgrounds. So we just think of G and B as a choice of the couplings for our sigma model. And in fact, what's written here is the most general Lorentz invariant, classically scale invariant scalar field theory in 1 plus 1 dimensions. And it has this kind of generally covariant structure with respect to field redefinitions. So you can think of the fields x mu as being coordinates on some target manifold. And then G and B are kind of naturally interpreted as geometric objects, a metric and a two form on the target space. So the couplings are specified by a choice of target space geometry. And we'll be interested in a special class of these models with the property of classical integrability. And I know a lot of people here are integrability experts. But so for us, we'll be, when we say integrability, we mean the existence of a lax representation. So that's a sort of formulation of the equations of motion as the flatness of some connection, which should depend in a non-trivial way on one complex parameter, the spectral parameter. And for anyone who's not an expert, the reason you would ask for this is sort of essentially that this property, this special form of an equation of motion, is associated in various ways with the solution of the system, with the sort of the ability to solve the system. So, for example, you can use this lax connection to construct non-local conserved charges, an infinite family of non-local conserved charges, and this kind of infinite symmetry algebra is associated with integrability. And this has been integrability has been very useful in the string theory context. So that's kind of one reason why you'd be interested in these integrable sigma models. In general, it's a very hard problem. If I hand you string theory on some curved background, say Schwarzschild, or Schwarzschild with some alpha prime corrections, it's a very hard problem for you to tell me the spectrum of the theory, which is a really basic observable. However, in integrable contexts, so integrable examples of curved spaces, like ADS 5 cross S5, great progress in that direction has been made using integrability techniques and other lower dimensional ADS examples. But in general, it's a very hard question to sort of classify which choices of G and B correspond to integrable theories. And this is sort of a general question that we're interested in. Which sigma models are integrable? In general, it's really hard to know how to construct a lax connection and to know whether one exists at all. So I said that these models are classically scale invariant, but at the quantum level, they'll have UV divergences, and they won't generically be scale invariant. So there'll be an RG flow, which we can understand as some kind of geometrical flow. So as I change the RG scale of the 2D theory, it's known in general that I stay in the class of sigma models, but the geometry changes. So I have some kind of squashing of some deformation of the target space geometry along the 2D RG flow. And this was worked out many years ago, back in 70s and 80s. So at the leading order, in the special case when the B field vanishes, the running of the metric is just given by its Ricci tensor. So that's what they call Ricci flow in the maths literature. And this actually just, this gets alpha prime corrections at every order. So this is the 2-loop correction. It's some kind of Riemann squared term, and there'll be an infinite number of corrections. So I've set alpha prime to 1 in this talk, but yeah, this term comes with 1 power of alpha prime, this one comes with 2 powers, and alpha prime is just counting loops. So there's one more term that I should explain here, which is this diffeomorphism term, nabla psi. So psi is a vector that you're kind of.
Sorry, can I ask a question? Which of these terms are universal, and which ones can you get rid of by diffeomorphisms?
By diffeomorphisms.
So I mean, normally you can do a reparametrization, and only the leading term is invariant, and you can just get rid of the rest.
Because this whole thing is sort of covariant, then it doesn't change under diffeomorphisms. But if you make diffeomorphisms that depend on the RG scale, then this term changes. So if I change coordinates, say I have some coupling which runs, if I change coordinates in a way that depends on that coupling, then this diffeomorphism term will change.
So can you get, how much of the rest can you get rid of if you do that?
None. But you could do other things like scheme change. So you could shift the metric by the Ricci tensor, and then this term will be invariant, but the 2-loop onwards terms won't be invariant.
So it's just like normal. The 1-loop term is the only term that's invariant under scheme changes.
Yeah, but as I'll say later, there are some special cases where the 2-loop term is also invariant. It's a bit like there's some analog of single coupling theories where the 2-loop coefficient is also invariant.
Okay, thank you.
Yeah. But so this term is somehow associated to diffeomorphisms, and essentially it corresponds to field renormalizations. So this is like making a diffeomorphism of the target space along the RG flow. So this is thought of, you can see this as a gauge transformation of the target space metric, which depends on the RG scale. And now going to this general case, so if I kind of reintroduce the B field, then things kind of generalize fairly straightforwardly. We'll use this particular subtraction scheme of Metsayev and Seitlin. So letting H be the field strength of the B field, you can construct a torsionful connection whose torsion is given by H. And the associated curvature gives a kind of nice way to package up the beta function. So I've written it here, and again at the leading order, at the 1-loop term is the sort of torsionful Ricci tensor, which is now not it's not symmetric. It's got an anti-symmetric part from the torsion. And the 2-loop term is some kind of Riemann squared and Riemann H squared, which I haven't written explicitly. So that's the running of the metric and the B field combined. So again, we still have this diffeomorphism term. That's like an infinitesimal gauge transformation corresponding to diffeomorphisms. And then we also have this exact 2-form term. So this is now the gauge transformation corresponding not to the metric, but to the B field, right? This is like shifting the B field by something exact. And so from the point of view of the sigma model, what does that mean? So shifting the B field by something exact, that just corresponds to adding a total derivative to the Lagrangian, right? So this term just parameterizes our kind of ambiguity in choosing a Lagrangian for a given action. So this is like shifting changing y is just like shifting the Lagrangian by a total derivative in a way that depends on RG scale. But these formulas are actually not very important. The key point is just to note that the space of couplings, G and B, is an infinite dimensional one, because they're functions of the fields X. So you could imagine Taylor expanding them in powers of X. And every Taylor coefficient is in principle an independent coupling that can run independently. So we'll be asking the question of when this infinite space of couplings can be truncated to a finite subspace in a way that's consistent with the RG flow. So which special choices of G and B correspond to renormalizable theories? Where renormalizable here means it means you can absorb the divergences into the running of a finite number of couplings. Any questions about that? No, okay. So let's say we want to build some renormalizable theories.
Sorry, actually, there is a question.
Yeah.
There was, I guess, following on Gerard's question. So suppose that you work in some set of coordinates x, and you think, okay, I can't have a finite number of couplings, but then someone cleverer comes along and says, but if you make a field redefinition of the x's that's super complicated or whatever, then it starts looking like it's a finite number of couplings. Can you really distinguish what it means to be something that only needs a finite number of couplings?
Yeah, I agree. It's a bit subtle, perhaps. It may be that you could choose some bad coordinates where you cannot see clearly that you could absorb the divergences into a finite number of couplings.
Okay.
Yeah.
Sorry, could I also say, so is there only one equation for both G and B, or two equations for G and B separate?
Yeah, so if you just project this guy into a symmetric part and anti-symmetric part,
okay,
then you get the running of G and running of B.
All right, B is anti-symmetric. Let's see.
Yeah, so G is symmetric and B is anti-symmetric.
So I also have a question. So if your question, G, B give renormalizable theories from the perspective of the target space or the string theory picture, what would that, does that property correspond to anything nice?
So in string theory, you need this sigma model to be conformal, right? So there's no.
That's just the vanishing of the bit. I thought that was, but that has nothing to do whether there's an infinite number of functions or a finite.
So we're talking about how many things run under RG, and in string theory, nothing should be running under RG of the sigma model.
Right.
So we're outside of the realm of string theory. We're just looking at bosonic sigma models, which in principle have nothing to do with string theory.
I see.
Yeah, so we're totally, the string context is a very special renormalizable case where nothing runs at all.
So I see. So you're not going to talk about conformal things here necessarily.
I'll mention them, but that's not really, not really.
Okay, good. Thank you.
Yeah, no worries.
Also, maybe one more question.
Sure.
But on previous slide, you kind of renormalized everything up to second loop, and you kind of removed all divergences, right? So,
sure.
so here you go. Even you have like infinite couplings, but they're all finite and all nice. So
sure.
Right.
Sure.
So then, what you call renormalizable? Because now you don't have any divergences.
Sure. I mean, I suppose what I want to call non-renormalizable is a bit nicer than some things which we call non-renormalizable, like Einstein theory. But yeah, I want to say that renormalizable is, by here, what I mean by renormalizable is this special thing where you can absorb the divergences into a finite number of couplings. So it's nice that even all these sigma models are known to, I mean, these beta functions were worked out in full generality. And it's nice that they stay in the class of sigma models. And so this RG flow is quite nice in general, but we want an even specialer case.
Yeah, all right, thanks.
So let's just try and build some renormalizable theories. And the tactic should be, I'm just going to throw in loads of symmetry, right? So I'll try and assume so much symmetry that the global symmetry alone will reduce this space of couplings to a finite dimensional one. And then assuming the RG flow respects this symmetry, then it should stay within this finite dimensional subspace. So then I should have guaranteed a renormalizable theory, right? So let's try. So I'll assume a scalar field which lives in a group G. And first I'll try assuming left and right global symmetry. And in fact, you can show that there are only two allowed terms respecting those symmetries. There's the usual principal chiral model term, and so that's a particular metric, and you're free to choose its radius. That's this parameter h. And there's a particular B field that's allowed, which is called the Vesumino term, which respects the symmetry. And so the Vesumino term has a quantized coefficient k if the group is compact. And those are the only allowed terms.
Are you assuming something about the number of derivatives?
Yeah, so we're assuming two derivatives everywhere. We're assuming actions of this form. Sorry,
yes.
Yeah.
Fair enough.
So these are the only allowed terms. And And I've written the structures of the geometry here, but it's not very important. And in this second case, where if I instead assume G global symmetry and H gauge symmetry, where H is a specially chosen subgroup so that the coset space G over H is symmetric space, then I only have one allowed term, which is the usual symmetric space geometry, just a metric with no B field allowed. And again, I'm free to choose the radius. So in both cases, I have one or two sort of free parameters, assuming that amount of symmetry. And indeed, it does give renormalizability. So in both those cases, I find that those complicated equations, this Ricci flow, and now with corrections at the subleading order, they're solved by just the running of these blue coupling constants, just a finite number of couplings. So in this first case, the quantized level K doesn't run, and the radius of the principal Cara model runs in this way. You can see here that this will vanish the special point when K and H are plus or minus each other. So that's the Vesemina-Witten model, which is conformal.
Sorry, except that there are finitely many, so the finitely many counterterms you can now add. What's the actual qualitative difference with the case when you have infinitely many of them? In the sense that you can also renormalize it, just you have lots of counterterms.
Yeah, that's it. Just here you can understand the running as just running of a couple of parameters. Okay. It's a kind of special case. It's not generic. And in this second case, you just have running of the radius. But something interesting happens when you try and throw in all this symmetry. You actually find that you've accidentally built integrable models. So these theories, principal Cara model with Vesemina term and the symmetric space sigma model, they're actually classically integrable, and they have lax connections. So somehow it seems that I got that for free. And this kind of leads me to the focus of this talk, which is a kind of conjecture, funny conjecture, that somehow integrability is related to this renormalizability property. So it's kind of the causation is sort of in that particular direction. So we kind of
so my previous question. So if you don't constrain the particular symmetry, right, you still have renormalizability, just very ugly. But it's obviously not integrable. So how does
you don't have renormalizability in the sense I want, which is finite number of running couplings.
So it's rather than renormalizability, you mean finite number of couplings?
Yeah.
Sorry. So is the conjecture that every time you have a finite number of couplings, the model is integrable?
No, it's the other way around. So the conjecture is that the real cause of renormalizability here is integrability. So it's like if you have integrability, then you will have renormalizability.
But there will be renormalizable models with a finite number of couplings that are not integrable.
Yeah, and so the converse doesn't seem to be true. And
so how does this help me?
Well, it tells you you can kind of
basically I have to find the integrable models first, and then you guarantee that they're renormalizable.
Yeah, but it tells you that you can kind of you can rule models out from being integrable if they're not renormalizable. And also, if you find a model and you think it might be integrable, then it's a good check, like, is it renormalizable? And it's also, I mean...
But sorry, conceptually, integrability is a much more specific, it's much harder to find an integrable theory, just naively.
Sure. But it's a kind of interesting property.
So it would be, so are you saying that there are no counterexamples to this, that if I... that I'm not going to be able to come up with an integrable model that is not renormalizable?
Yeah, and the interesting thing is that the pattern we see is that
right. there must be plenty of classically integrable sigma models that are not renormalizable.
Well, please tell me one.
Really? No, I don't know. I'm just
I don't know any.
By the way, one of the well-known examples is the CPN sigma model.
Exactly.
But I think it's classically it's integrable, but quantum mechanically
exactly.
Not.
Exactly.
This will be one loop renormalizable. No?
Huh?
I think this model will be one loop renormalizable.
Oh, but one loop.
Yeah. So maybe a more refined conjecture is classically integrable sigma models should be one loop renormalizable. But this already is very interesting because It's very
But
strange.
sorry, I'm still like
Sorry.
unhappy. How do you define number of couplings still? It's kind of subjective, right? You just say, oh, that's an arbitrary function, so it is like infinitely many couplings. But actually, if you expand this function in a good enough basis, it could then be finitely many of these couplings, right? Who knows?
Yeah, you could say everything. RG flow is just a line of theories, so it's always one coupling.
Yeah, what I'm saying, so you have this RG flow, right? If you have some starting point with certain properties, not necessarily symmetric space, but some properties, I don't know how to classify them. It could happen that if you expand your infinitely many couplings in some particular basis, only finitely many of the coefficients actually flow, right? Yeah. So, but that's very hard to.
Yeah, so it's about choosing. Yeah, you have to choose the right basis. Yeah, if there exists a basis, then we say it's renormalizable. If there exists a choice of basis of couplings where only finite number run.
Although this conjecture is very hard to check, then.
Yeah, I suppose. Imagine you take a principal Cairo model, and you write it in some messed up coordinates where symmetries are completely invisible. No, but actually, you would still find only running of the overall radius, but it may be that you'd have to find some very messy diffeomorphism vector. So I guess that's where it will happen. That this diffeomorphism vector will become some very messy thing that you need to find. And if you chose very bad coordinates, then so in every case when we say renormalizable, we mean like renormalizable with finite many running couplings and some diffeomorphism vector. So this will become a mess if you pick bad coordinates. But it's quite surprising that this classical property, integrability, seems to lead to some special one loop RG behavior. It's not that surprising because one loop is kind of mostly determined by the equations of motion, but it's still kind of surprising. So it's actually not really a very new idea actually, and sort of in the spirit of this conjecture goes back a long way to the 90s when these people, Fatiev and collaborators, they actually discovered integrable sigma models in this way. Well, so in particular, I'm thinking of the 2D sausage model. So there they had some particular, this trigonometric S matrix, exact integrable S matrix, and they wanted to find the semi-classical sigma model description. And their philosophy was basically, although it's not really said in these words, but they kind of assume that since it's integrable, it needs to, it should be solving this Ricci flow, this RG equation, with only a couple of parameters running. So they basically assume this conjecture, and they solve the Ricci flow to find some particular geometry, and then they match it up in some way with the S matrix. So it's a kind of old idea, and in fact, that geometry that they found wasn't found to be classically integrable in our sense, having a lax connection, until much later, this paper of Lukyanov. So they really discovered the model using this RG flow. But the exact sort of the reason why this should be true, that integrability should lead to renormalizability, is not well understood. We don't really know how, but I can give you some intuition. So the intuition is that you want to land on some particular theory in the infrared, which is described by some exact S matrix, say in many integrable theories. And the exact S matrix has some finite number of parameters. And so if you start with some weakly coupled sigma model in the UV, you don't expect to pick up an infinite number of independent coupling constants as you flow down along the RG. Because you need to land on this particular integrable dynamics in the infrared. And
sorry, wouldn't there be in general many different UV models which could flow to the same? I mean, in some universality class, right? Of models that would all flow to some nice IR matrix. Is that intuition somehow wrong?
I don't know.
Well, there should be an infinite space of irrelevant perturbations away from, well, relevant, whichever it is.
And many of them are not going to be integrable, presumably.
Sure.
Yeah, but he's not discussing integrability at the quantum level. I think he links classical integrability with this renormalizability.
But along the whole path in your story, Nat, the theory is integrable along the whole renormalization flow.
Well,
is that right?
Somehow what we're doing is very semi-classical. It's like first or second order in loop expansion. So I don't really have control over the RG flow. But yeah, I suppose.
So I see. So I should really just think about a little neighborhood near this IR fixed point.
Yeah.
In energy scales, and you're picking out integrable directions along it.
Yeah. So what we're studying is probably you can think of it more as we're like maybe the picture is more like you have some UV weakly coupled theory, and we're in the UV studying some theory, some weakly coupled semi-classical expansion, but we have in mind that we want this this RG flow to sort of land on something particular in the IR. So you're in trouble if you're already picking up, at first or second order in this expansion. The semi-classical expansion, you're kind of in trouble if you're picking up some infinite number of couplings, which seem to be independent. But it's just a very loose intuition. But so, yeah.
What about the UV description of the non-renormalizable models? So the renormalizable ones are like relevant perturbations of some CFT. And what happens to the non-renormalizable ones in the UV?
Well, I mean, really, I'm reducing things to sort of a simpler case than they generally are. Because in general, like these things don't have to be weakly coupled in the UV or anything like that. So some of them are sort of really badly behaved in the UV. And so, for example, if you put, if you just reverse the sign of the curvature, so you go from, instead of sphere, you go to like hyperboloid, then it's strongly coupled in the UV. So I'm reducing to some simple case. But yeah, if you assume some sort of some particular conditions, then even if it's not renormalizable, it will be weakly coupled. So it's sort of like it will still be some weakly coupled theory in the UV, but it has it just has a more complicated structure. So it's not just like one running coupling.
Okay, thanks. How can it? No, I wondered how can it have infinitely many couplings? If you see it from the UV as a perturbation, does it mean you have?
Sorry, could I suggest when you ask a question, could you turn on camera, because otherwise it looks a bit dead.
Well, yeah, I don't know. I don't really know how to think about this in the language of perturbations of CFT. Yeah, I think it's a bit more.
Yeah.
It's maybe a bit more subtle. This point about whether the number of running couplings is finite or infinite. Yeah. I don't know what to say about this. But so one more piece of intuition about why this could be true is that we have this, in general, an infinite number of couplings, and you can try and use symmetry to reduce to some finite subspace, and so you'll need an infinite number of symmetries to go from infinite to finite. So this seems like it kind of smells of integrability. Yeah, any more questions about this conjecture, about this idea?
So I'm confused. I thought the infinite number of charges would let you give an infinite number of deformations of the S matrix.
Sorry?
An infinite number of charges should allow you to deform the S matrix in an infinite number of ways.
I'm not sure I understand what you mean.
Do you mean by CDD factors, or?
Yeah, like TT bar, you can just.
So the picture I have in mind is quite simple. It's like I have some theory which has some integrable structure. It has classically it has a infinite family of commuting charges, and let's say I assume that this structure kind of persists in some way at the quantum level. I can somehow quantize the theory, keeping some of this structure, and then I just see that this will give some strict constraints on the RG flow, because the quantum theory has to respect this integrable structure, and this could be these constraints could be the ones that will give you exactly this renormalizability property. Does that make sense? So I mean, relation to S matrix is like really a bit far off. That's a very distant point. We're kind of quite far from linking to infrared S matrix. Okay.
Yeah, so I guess let's move on.
Yeah. So we're kind of interested in checking if this conjecture is true, and it's previously only been tested at one loop order. So our aim was to test the relationship between integrability and renormalizability, starting from two loops. And actually, we'll see that things have become kind of non-trivial when you go beyond one loop. But so we'll need some non-trivial examples to make this test. And these should be integrable models with less global symmetry. Because in these cases we looked at before, we saw that global symmetry was a kind of common cause of integrability and renormalizability. Right? The global symmetry was so strong that, that you kind of got both of these things. And the idea is that when you take away this global symmetry, if you have integrability, you will still have renormalizability. So we need some integrable models with less global symmetry. And the examples we'll use are the lambda and eta deformations. And I'll introduce them in a minute. So the plan of the talk is two parts. First, I'm going to review what's known at the one loop order, sort of old things, and then I'll talk about new things. So what we've found at higher loop orders, and first I'll talk about this, what we called the tripled description of the lambda model, and then I'll talk about the moving to the physical target space. And I'll just introduce some notation before I move on. I'll refer to the Vesemina-Witten model on a group G as L subscript G, and the gauged version, the gauged Vesemina-Witten model, as L subscript G over H, where H is some subgroup which you can gauge. So the number of degrees of freedom of this gauged model is like G minus H, and you can write it in terms of a scalar in the big group and a vector field in the algebra of the subgroup. So let me introduce the lambda model. I've written its Lagrangian here, and it looks kind of like a deformation of this term. So this term alone would be a kind of topological theory. It's G over G gauged Vesemina-Witten model. It's like gauging away the whole group. So it kind of has no degrees of freedom. But when you deform by this A squared term, you break the gauge symmetry. So adding this deformation with parameter gamma kind of gives back degrees of freedom because I break the gauge symmetry. And there's two cases that I want to introduce in parallel here. The lambda model built on a group or on a symmetric space. So in the group case, I deform here by the whole of A squared. So P is just 1. And in the symmetric space case, it's just the projector P is just picking out the coset part of A. So in the group case, I break all the gauge symmetry. Whereas in the symmetric space case, I just break the H subgroup. I just break the coset part of the gauge symmetry, and I leave the H subgroup. So in the group case, I have the full G degrees of freedom in this model. And in the symmetric space case, I still have H gauge symmetry. So I have the same number of degrees of freedom as a symmetric space, G minus H.
Sorry, what is A plus minus again?
So this model depends on a scalar in the group, and here this vector field A plus and minus are just 2D light cone coordinates. So this is a 2D gauge field, and it lives in the algebra of the group, the full group. So somehow the kind of symmetric space structure in that case comes from the projector. So A lives in the full group, but this projector kind of picks out a subgroup.
So A is like a vector. No. So it's like a current of G or not?
No, A is not flat. It's just a vector field.
And then what? P? What was P again?
So P is, there's two cases. P is either 1 or it's a projector onto the coset part of the algebra. So later on, we will use a redefined version of gamma, which is called kappa. There's a lot of, the deformation parameters in this subject are there's lots of different names. So the key point about this model is that it's classically integrable. And so yeah, Collier was asking about this vector field. You might say, like, what are you doing? You're supposed to talk about sigma models. And this is not a sigma model because it has a gauge field. But the point here is that the gauge fields, they're not dynamical. They don't have any derivatives. So you can just integrate them out. And you obtain a sigma model, which just depends on the scalar G, written here. So it's like a Wessimino-Witten model plus some current term. J plus and K minus are the holomorphic currents, holomorphic anti-holomorphic currents of the Wessimino-Witten model. And I put some funny matrix M in the middle, M inverse, which depends on G in some complicated way.
So what's the metric look like in this sigma model?
Well, so I haven't written it very explicitly. It's something fairly complicated.
Is it regular?
Is it regular?
Are there strong curvature regions?
I think it is regular.
So
maybe I don't want to commit that 100%. Yeah, it should be regular. So
there are no regions with strong curvature in target space. Is this the model you're going to obtain through some T-duality?
No.
Okay, maybe this is different then. Okay.
Yeah, I'm not sure about that actually. I think it is regular, but I'm not sure 100%.
You know, because I guess I'm asking because if it has regions of strong curvature, then we can't really trust the classical description at all, and there will be significant corrections near those regions.
Sure.
So
sure.
It would be nice to know how we can trust this.
Sure.
Anyway,
but really, you can think about picking whichever point you like in the target space and doing this there in a neighborhood at this point. So it's really, you're kind of safe. You can just pick a generic point and sort of do things in a neighborhood of that point.
Sorry, I have more naive. Sorry.
So sorry, Nat. I think you assume here that your metric is indeed regular. Otherwise, I think Bogdan is right. Since this is a topological prescription, you cannot really have these regions, right? And then this is just.
Well, I mean, this applies. You can do all of this whole story just with local geometry. So I don't think we need to. I don't think we need to assume regularity. I just do things locally in a patch.
Okay.
No, but I mean, okay. I mean, you can play that game, but if you really want to ask the physical theory, you need to know the whole space. And I mean, it's like if you pick some sort of.
Yeah. Sorry.
This is not classically integrable.
Sorry.
No, I mean, so you are all the you consider the remaining in the vicinity, in some vicinity, right?
Yeah, you can. Okay. Maybe we can discuss this later. Maybe.
So, sorry, could I have a silly question? So, what about what happened? What about Lorentz invariance? Because I don't understand how the Lorentz structure works. It's like G plus and K minus, but
yeah. So plus index means it has weight 1 under like SO1 comma 1, and minus means it has weight -1. So this time is Lorentz invariant, and this time is also Lorentz invariant separately.
But shouldn't it be also J minus K plus term to make it actual Lorentz invariant?
No, this is Lorentz invariant on its own. So plus gets rotated one way, minus the other, and they cancel. So like p squared is like p plus p minus in like-hand coordinates. So p squared is Lorentz invariant.
Yeah, p squared. Yeah, I understand that. If it's two different fields,
sorry. Yeah, so this is like terms. Yeah, you can use epsilon as well. So this would be like eta epsilon. Okay. So I kind of time is going much faster than I thought. So
okay, there were a lot of questions.
Yeah, that's fine. But so I introduced this model like a deformation of this gamma equals 0 point, which is topological. It's sort of more natural to think of it as a deformation of the opposite point, gamma equals infinity. So this point, at this point, this term blows up, and A is forced to vanish, or the projected part of A is forced to vanish as a delta function. And so this, if you kill all of A in the group case, then this term just reduces to the usual Westermüller-Witten model. You just set A to 0. And in the symmetric space case, this sets A to be valued in the subalgebra of H. And if you plug that in here, then you just get the G over H gauged Westermüller-Witten model. So in either case, you get a gauged or ungauged Westermüller-Witten model. And that's a CFT. And the sort of nice thing about this point is that it has the same number of degrees of freedom as generic gamma. It's not a degenerate point, like gamma equals 0. But for general values of gamma, this is not a conformal theory. We will have an RG flow, which we'll see later. And the key point is we wanted to make integrable models with less global symmetry. And indeed, these models have much less global symmetry than other examples. So certainly the global symmetry here alone doesn't force you to be in some finite dimensional space of models. In the group case, we just have G global symmetry. And in the coset case, we have no global symmetry at all. So one nice thing about this lambda model is that it allows you to probe non-abelian duality, because there's a particular limit in parameter space, and also zooming in on the identity element of the group, when this lambda model becomes the interpolating model for non-abelian duality. So I have a slide explaining non-abelian duality, but I think I'll skip it because we're kind of low on time. But basically, this interpolating model for non-abelian duality, it works like this. V is a Lagrange multiplier field. So V is what became of G in this zooming in process. And if you integrate out V, then A is flat. It forces that constraint. So that just brings this term back to the principal chiral model or symmetric space in either case. And if on the other hand you integrate out A, which is just Gaussian, it only appears quadratically, then you get some sigma model in terms of V, and that's called the non-abelian dual theory. So
this non-abelian dual theory, you could just think of that you're doing some non-abelian T-duality, right?
That's what I mean, non-abelian T-duality, yeah.
Right. Usually these things have some fixed points in their orbits where things become singular, right? Or am I misremembering?
Yeah, maybe, but yeah. But as I said, I don't think it's not really
no, but
this.
Well, but if at this special point, so what you're saying is that this model that you're studying at some particular fixed point, at some particular point, becomes like the non-abelian dual of something. And so at this special point, certainly there will be regions in target space with target space curvature that will be large.
Sure. And so I just pick a different point, and I
no, but that's like saying, well, I mean, okay, so if you pick a different point, that's like doing a sigma model on Schwarzschild or something, and then expanding at some points will be perfectly reasonable,
okay. I mean,
and at many other points it will not be reasonable.
I take Schwarzschild as a perfectly okay example. Schwarzschild would be an example that's one loop conformal. It's Ricci flat.
But I mean, you can't believe that that really describes the physics, right? The one loop sigma model of Schwarzschild will receive strong corrections.
The Schwarzschild is an okay string background at one loop order. It gets alpha.
That's right, but exactly, it gets alpha prime corrected, right? And presumably, as you go into regions with strong curvature, those corrections become more and more important, and 2 and 3 and 4 and 5 loop corrections become more and more important.
So you can't trust this expansion near the singularity. Sure.
So therefore, for any background which has got some regions of target space curvature, where the target space curvature is high, you can't really trust. I mean,
I'm just saying
there's one loop expansion, but it isn't going to capture any physics.
Sure, I'm just claiming there is some meaning to the statement that Schwarzschild is a string background at the leading order. There's some meaning to that statement, and it means something away from the singularity. And there's the same kind of statement I want to make here, but it's not about being a string background. It's not about being conformal. It's about.
I mean, the other problem that you have, so Schwarzschild at least has got a horizon, and it's not clear that here you would have a horizon which shields the singularities. So in a lot of, I don't know if in specifically this deformation that you have
kind of far off concern. I mean, we're not in string.
But that's a really important concern, right?
We're not in
if you have a target, but surely it must be true. Yeah, are you saying it's different for sigma models? That sigma models could be consistent on target spaces with regions where the target space singularity is target space curvature is large?
Yeah, in fact, it's true that if you just start with this one loop Ricci flow, it's true that generic geometries will develop curvatures after finite RG time.
Mm-hmm.
So I see it as okay. But maybe let's talk about this at the end.
Yeah, okay.
I'm a bit worried about time.
I'm concerned that you're not going to capture the
But
physics.
I thought the initial motivation was kind of quite formal. So let's compute two loops and then see whether like the parameter space is still finite and whether it's linked to integrability, whether it has anything to do with physics. I think it wasn't really even in the motivation. Yes, correct.
Yeah.
Okay. If we're not making any physical claims, then I'm happy.
But it's maybe you can think of it as like a diagnostic tool for integrability. Yeah. But so let's kind of move on. Let's talk about this at the end. But so yeah, I will, because I'm very short on time, I'll just skip this eta-model stuff. There's another example of integrable sigma models, integrable deformations, which have less global symmetry, another class called eta-models. So very surprisingly, these models, let's say the lambda model, which is the only one I've kind of talked about, they are found to be renormalizable at one loop order with just this deformation parameter gamma, or here redefined version kappa, just that parameter running. So this complicated equation, this Ricci flow equation, the one loop RG equation, is solved by just this one parameter running. So it's a very special conspiracy in the geometry for this to happen. And this is kind of remarkable test of this conjecture. This is kind of why we believe this to be true, but one of the reasons why. We don't see any other good reason why this happens. It's totally non-generic that things can be phrased in this way. So we believe that the reason for this happening is integrability. I've written the questions in.
So this deformed model, is it still in the same class where you have two fields G and B in principle? Can you write it?
Yeah, I haven't written G and B kind of explicitly because it's a bit of a mess.
Yeah.
You can rewrite all this in terms of metric and a B field. So this guy will have metric and B field contributions because, as we said, it's made out of eta plus epsilon. Yes. So this is kind of very funny that this happens. And so our question is, what happens at higher loop orders? does this persist beyond one loop? So this is, I'm now kind of starting with the more recent stuff from October. I want to claim that this pattern does persist at higher loop orders. And for the lambda model, I'll try to prove to you that, that the theory with the gauge field, L of G and A, is renormalizable at all loop orders. And we'll see that the difficulties will come in when you try to integrate out A. Maybe this is a good moment for a quick break.
So let's have a tea/coffee break for 7 minutes.
Sure.
So 11:05, we're back.
Sure. With fields G tilde, H hat, and H bar. And we've derived it at the level of the path integral. So we know that this model is sort of quantum equivalent to the lambda model, L of G and A. So as I said, this decoupled theory, this decoupled Lagrangian term, this Vestumiano-Witten model is conformal on its own. So it just tells us that its coefficient shouldn't run under RG. And then the rest of the RG flow is totally determined by L prime. The rest
Sorry, so just a question about going between these models. A has no derivatives, but HDH has got a derivative. So you're changing the number of derivatives? Or rather, one is local with respect to the other, one is non-local if you go backwards?
Yeah, so it's sort of non-local field redefinition. Because it has derivatives, yeah.
So should I be worried about a non-local field redefinition?
So no, but it just means you have to account for it with a Jacobian.
Oh, well, okay. I mean, how do I know that the loop expansion in one is the same as the loop expansion in the other?
Well, it's an expansion in the same parameter of this basically same path integral. So I mean, it's like I just changed integration variables.
Okay, I'm not sure. Anyway, maybe we come back to that later.
Sure. So the RG flow is totally determined by this part, L prime. So what is L prime? It's a Vestumiano-Witten model on a product of G cross G with this negative level, minus K plus 2 CG, perturbed by some interaction between the two Vestumiano-Witten models. And it's actually a model which has appeared before, back in the 90s, in this paper. And also more recently, it's a special case of what Svetsos and collaborators called the doubly deformed lambda model. And the kind of central point for us is that this model, L prime, has lots of symmetry, lots of global symmetry. So it has G cross G holomorphic, cross G anti-holomorphic symmetry, acting in this way. So it has something funny has happened because this model has much more symmetry, much more global symmetry than the lambda model that we started with. And somehow the idea is that somehow in going to this sort of triple description,
but you also have more fields, right, or not?
Yeah, you add extra fields. You're kind of like linearizing some symmetries. You're kind of or maybe some symmetries.
Well, you can always extend your symmetry as large as you want if you add more fields. So it's not very surprising.
Well, yeah, maybe. But the symmetry gives you exactly what you want here, because L prime is actually the only Lagrangian with this symmetry, with this number of fields. So the symmetry fixes L prime uniquely up to the choice of the coefficients, K and gamma. And then we're just back in the case we started with, like the principal Caron model. The symmetry forces you to be in a finite dimensional space of models, so it must be renormalizable. And that should apply to all orders in the loop expansion.
Sorry, can you make that last point again?
So the symmetry constrains, the global symmetry of this model constrains it to take exactly this form with only freedom basically to choose one parameter because K is quantized. So only one, so if assuming the symmetry is respected by the RG flow, then the RG flow must stay within this class of Lagrangians.
And why should the RG flow not break the symmetry?
Well, that's a good question. For this part, just G, it's pretty obvious because we know that at all orders in this beta function, the beta coefficients are just made of like they're made of these covariant objects like Riemann tensor, H flux, and these things respect the symmetry, assuming the geometry does. But with these, this kind of affine Catch-Moody part, it's maybe a bit subtle and not completely clear from first principles that this should be preserved by the RG flow. But let's say it's something we believe. Maybe if you kind of think of the case of Westermino-Witten model, where this symmetry is preserved at the quantum level. But yeah, I think this is not completely clear. But we checked explicitly at two-loop order. And so a direct computation shows that this theory is indeed two-loop renormalizable with this beta function. So the new term is this blue term here. And you get the expected fixed points at particular values of kappa. And I just want to mention that in the non-abelian dual limit, so when the lambda model becomes that interpolating model for non-abelian duality, we find that that interpolating model is two-loop renormalizable, and its two-loop beta function exactly matches that of the principal chiral model from the old literature. So that was all for the group lambda model, and everything goes through basically the same for the symmetric space lambda model.
Sorry. Beta function at two loops is already scheme dependent.
Yeah,
so is there any significance in the fact that it exactly matches them at two loops?
Yeah, I'll comment on this on the next slide. But just to say before I mention that that the symmetric space works exactly the same. So the configuration space is again G cross G cross G, but now with an H gauge symmetry. And again, you can argue that it should be renormalizable due to symmetries, which extra manifest symmetries. At two loops, a direct computation gives these beta functions. And again, in the non-abelian dual limit, we reproduce the two-loop beta function of the symmetric space model. So yeah, about coupling redefinitions and scheme change. So yeah, generally, as you say, under a coupling redefinition, the one-loop beta coefficients are invariant, but the two-loop ones aren't. So you might say, like, what's the meaning of this blue term? It doesn't mean anything. But actually, I claim there is still some invariant information in that term, because in single coupling theories, the two-loop beta coefficient is also invariant. And there is a sort of important single coupling limit, which is this one, this non-abelian dual limit, where there's only one coupling H. So I claim that the invariant information in this term is precisely this information. So we recover this, and this beta function is scheme independent.
Sorry, Nat, just maybe a general point.
Yeah.
Have you or anybody tried quantum reduction of any of those your proposed cassette models, like Drinfeld-Sokolov or something, which would lead to deformed Suzuki-Katsama or something like this? I'm just curious if these patterns can be observed in those models. So what immediately would imply at the quantum level?
I don't know. I don't know.
Okay.
Sorry. So taking away from this tripled formalism story, we found that this lambda model with the gauge field seems, on a general argument, it seems like it should be renormalizable at all loop orders, assuming that these holomorphic and anti-holomorphic symmetries don't get broken. And we checked that to two loops and computed the beta functions. And in the non-abelian dual limit, we match up exactly with these known two-loop beta functions for the original models. So for the principal chiral model and the symmetric space sigma model. But now we want to understand how to move to the physical target space. So this is just the question of how to integrate out the gauge field A. So we have this lambda model. I've written it more explicitly here. And you want to do the integral over A. And you might just think, oh, I can do it classically, as I kind of told you earlier, because A is not dynamical. It's just Gaussian. But the model you get, this lambda model, this classical lambda model, is actually not two-loop renormalizable. So somehow you screw things up when you do that. It's pretty strange. And you can check, say, just in the simplest 2D example, this 2D target space, SO3 over SO2, that lambda model. You can check that this model is not renormalizable at two-loop order with just kappa running. So something's gone wrong.
But is that related to my question about A now being written in terms of an extra derivative?
So I don't think so. I think it's because we were too hasty, and there's a Jacobian from integrating out A. So there's A appears, the quadratic term in A has this matrix in the middle, which depends on G. So it's going to give some Jacobian depending on G. And it's actually a bit subtle how to define such a Jacobian, because this operator M is not a nice operator. It's not like a Laplacian or something. It's just a number. It's not derivatives. So it's a kind of subtle thing. But we recall a particular prescription from the 90s, which was consistent with T-duality, where such integrals appear. And so their prescription now on a curved world sheet for this Gaussian integral over a 2D vector field is given here. So there's this dilaton term, which is very important in T-duality. Of course, when we go to the flat world sheet, that vanishes. The Ricci scalar vanishes. But we still get this blue term, -1/2 d log det m squared. So this prescription for the evaluation of that integral suggests a particular counterterm to the Lagrangian.
Could you give any motivation for this? Because it's highly non-trivial that you do that. No?
To do this integral. So I think what they do in this paper, their kind of trick is to evaluate this integral by writing A plus as the plus derivative of some scalar field, U, and A minus as the minus derivative of some scalar field, another one, V. And then you integrate like scalars, and you have a nicer operator in the middle with D plus and D minus.
But why is that a better way than just integrating A plus and A minus? Like you can do lots of crazy things. Why this way is the right one?
Yeah. But this prescription was found to be good for T-duality. Yeah, I think it's not clear that that's the right way to do it. And in fact, it will become clear later on that that's actually the wrong way to do it. And we don't know how, really. We don't really know how to do it. But so it suggests some particular counterterm. This counterterm, you can see it's this quantum term because it comes with 1 over k compared to the classical Lagrangian, which comes with a power of k. So k is like 1 over k is counting loops. And it's something squared, so you should interpret it as like a quantum correction to the metric. It's an alpha prime correction to the metric. So this is like a finite counterterm, and this Lagrangian is like a particular choice of bare Lagrangian with a particular finite counterterm. So let's try that in this simple 2D target space example I showed you before. It gives this particular blue term as a counterterm. And indeed, I find that exactly restores the two-loop renormalizability that I wanted. So this theory, without the blue term, is not two-loop renormalizable in any subtraction scheme. You can prove this. But with this term, it is. So it's a kind of scheme invariant comment. So it's renormalizable at two loops with some particular diffeomorphism vector. And you get some two-loop beta functions that match the tripled formalism results after some coupling redefinition. So
and what does that term do to the metric? So, does it do something nice? I mean, I don't want to have to do this derivative and figure out what the metric is now. Maybe you can help me. I mean, the metric for the uncorrected geometry looks really bad.
Yeah. So I guess it does certainly have singularities. Yeah. That's clear.
And does this term
singularity double?
It gives more factors 1 over p squared minus q squared downstairs. It gives some particular corrections.
But you still will have this singularity.
Yeah, yeah.
Well, it gets worse, right?
Yeah,
yeah, exactly.
It's worse. Yeah. Just to say,
Not
I mean,
really a correction, right? It's
maybe
like
this will make you more happy.
Well, that's. But I think that's what I was trying to say. There is a singularity, and you go and try to make it better, but you'll make it worse.
But so, a particular limit of this geometry, kappa equals 1, is the SO3 over SO2 gauge Witten model. So it's very, something we're all comfortable with, something we were brought up with, and in that limit, this guy becomes, it doesn't depend on kappa, right? So it's exactly the correction, the leading alpha prime correction, which we all know is correct in the gauge Witten model, and you need this correction for the model to be conformal at 2-loop order. So here, as we move away from kappa equals 1, we no longer have conformality, but you need this correction now for renormalizability at the 2-loop order. So yeah, all these problems about singularities, they apply also to gauge Witten models, if they're problems. I can't hear you, you're on mute.
I mean, they are problems, right?
Well, there's the same problems. But so yeah, what I want to say is,
so our question, will it be reasonable to finish in like 10, 15 minutes?
Sorry, yeah, 10, 15 minutes. Yeah, sorry, I'm really running over a bit. So what I want to say is that it's not funny to have corrections to the geometry. These are just some particular finite local counterterms. And it's a normal thing that for Ward identities of global symmetries, to satisfy them at the quantum level, you may need some particular finite counterterms. And here we imagine that there's some hidden integrability, non-locally acting symmetries, whose Ward identities we're restoring at the quantum level with these counterterms. And we imagine, although it is just kind of fantasy at this point, we imagine that those hidden integrability symmetries are what's keeping the theory renormalizable. So in a sense, you may think that this is like the say leading in some expansion. This is like the kind of quantum integrable choice of bare action. But this is kind of hand-wavy statement. But so if we go up one level of complexity to a 3D example, lambda model based on SU2, we find, unfortunately, that things are more complicated, and this d log det m squared counterterm doesn't work. So the theory is not 2-loop renormalizable with that counterterm. It seems you need some more general counterterms above 2D, and that kind of makes sense. Like maybe there's the proper evaluation of this, the correct evaluation of this integral over A is different. But for a 2D target space, it kind of degenerates in some way and becomes this simple form, d log det m squared. So in that specific example of SU2, we found some complicated set of counterterms which give 2-loop renormalizability. I'll just quickly show you now, since we have 15 minutes. Here they are. It's a mess. We just found these ad hoc. I'm just showing them to you. I mean, I probably shouldn't show anyone this. The black terms are classical terms, and the blue terms are the counterterms. So it's a mess. We just found some particular, in some coordinates, we found these terms. We had some rationale for choosing them, but we don't have any real sense of what the general structure is. So it's kind of open question. What should be the general structure of the counterterms in this physical target space? Basically, how should you properly do the integral over A? That's the question. That's the open question. Any questions about this? No. Okay. So we have kind of 10 minutes, or should I be quicker?
Sorry, but why do you need to integrate out A before you actually proceed to the perturbation theory? Can't you just
you don't need
include these fields and?
Yeah, you can just include them, and then basically then we have this kind of trick, which means we can get back to a sigma model, which is to go to this triple language, just field redefinition of A, And then we know all the beta functions for sigma models, so it's easy to do calculations. So basically we're effectively doing a computation for this model, and we find that it's renormalizable. You might say, yeah, whatever, don't bother integrating out A. But there are other models, not the lambda model, say eta model, where you never had A in the first place, and you have the same problems. Maybe I'll just talk quickly about the eta model. So for eta model, which is another class of these integrable sigma models, classically integrable models with not much global symmetry, we have studied only the simplest target space, which is the 2D coset SO3 over SO2. Here's the geometry. So B field vanishes locally in 2D target space. And so this is for negative kappa squared, this is what Fatiev and collaborators discovered. This is this squashed sphere. It's a 2D sausage. So it's like, for kappa equals 0, it's a 2 sphere. It's just some particular coordinates for the 2 sphere. And as you turn on kappa, it's a sort of squashing sausage. And at kappa squared equals -1, it's sort of infinitely squashed, and it becomes a flat cylinder. There's this maximal deformation limit where it becomes, it's sort of extreme deformation where it becomes an analytically continued coset, H2. If you take this kappa squared to -1 limit in a different way, you don't go at a generic point, but you zoom in on one of the endpoints of the sausage, then you instead get something non-trivial. You get a gauged Westermüller-Witten model on an analytically continued coset. And so certainly funny things are happening here with signatures and stuff. So it's pretty formal, but yeah, so it makes sense. You should still get something conformal because these two things are the same from the point of view of beta functions, just doing different things with coordinates. So the nice thing is we have all this boundary data, these particular limits, and in all those limits, we know the form of all the alpha prime corrections. So for these three, there are actually no alpha prime corrections. They're all renormalizable without corrections. And for this example, the gauged Westermüller-Witten model, we know the form of the corrections to all orders by some general arguments from the 90s. So they're like this. The level gets shifted, and this tanh squared factor gets inverted, shifted, and inverted again. Now, if you expand that in powers of 1 over k, it's an infinite expansion. So we just copied this structure to make some ansatz for the form of the corrections to the eta model. So you see here, we take this geometry, we shift this overall coefficient by something, and for this factor, this coefficient of this isometry direction, we invert it, shift it, and invert it again. And we make sure that these shifts match up exactly with those shifts in the limit when they become the same, when this eta model becomes the gauged Westermüller-Witten model. And we also made sure that they match up with all of these other limits. So in those limits, they have to the corrections have to vanish. And you actually find if you try and get all those things that there aren't many things you can write down. I don't want to claim like uniqueness or anything, but it's fairly constrained. So it matches all the boundary data. And indeed, we checked a 3-loop order that this geometry with these particular corrections is 3-loop renormalizable in some natural subtraction scheme defined by the property that the RG invariant, this theory has some RG invariant ratio of 2 parameters, doesn't get any corrections. And we get some particular 3-loop beta functions. The new terms are in blue. And I just want to say that, just a comment, that another check is that there's some particular limit when the lambda model becomes the eta model. And we get matching between this geometry and the geometry we found for the lambda model. A kind of final push into the realm of the unknown is to just comment that these beta functions in this natural scheme, where the RG invariant doesn't get corrections, they have a kind of geometric series looking structure. So we have a conjecture that in this natural scheme at every order, in which the RG invariant doesn't get corrected, the beta functions can be resummed in this way. So this is like a conjecture for the all-loop beta functions in some scheme. But so just a comment about scheme change, again, there's another type of scheme change, not redefining the coupling constants, but instead making covariant shift of the geometry. So say shifting geometry by something with alpha prime, like shifting metric by a multiple of the Ricci tensor. So doing this basically changes the subtraction scheme. And you know, we've been working in this particular Metsayev-Zeitlin minimal scheme. So in general, the one-loop beta functions will be invariant under such shifts, but the two-loop ones won't. So that's, you know, this term won't be invariant. But in the special 2D case that we're in, or in fact in any example where the B field vanishes, you can show by general arguments, and it's in the appendix of our paper, that the two-loop terms will also be invariant if the B field vanishes. So that means that the renormalizability of the leading correction in here, the leading blue term at two-loop order, is scheme independent, and these leading terms in the beta functions are scheme independent. So let me kind of finish here with some conclusions. So it seems like this pattern that integrability gives renormalizability, only finitely many running couplings, this special behavior under RG, that seems to be true still at higher loop orders. But in general, you need to supplement the bare Lagrangians of these classically integrable sigma models with some specific finite counterterms, which you can interpret as quantum corrections to the geometry, alpha prime corrections, like in conformal examples. And since our work, since our papers, there were some more recent works where similar alpha prime corrections were found for similar integrable deformations in conformal examples, some particular homogeneous Young-Baxter deformations. So in some kind of low-dimensional 2D and 3D target spaces, we found the form of these corrections explicitly. And for general groups in symmetric spaces, so sort of covering all groups in symmetric spaces at once, we showed by general argument that this tripled lambda model, so that basically equivalent at the level of the path integral to the lambda model with the gauge field, is renormalizable at all loop orders without corrections. So in a way, it seems like this is the proper way to define the quantum theory. You know, if you believe this conjecture, then this is the proper way to define the quantum integrable theory, keeping the gauge field. And I'll just say something about non-abelian duality. So in that spirit, you should try to maybe define the non-abelian dual models as they're sort of properly defined by the interpolating model, the model with the gauge field. And that means that we're essentially computing the two-loop beta functions for the non-abelian dual models of the principal Chiral model and the symmetric space. So we conclude that the non-abelian dual models have the same beta functions and renormalizability properties as the original models. So non-abelian duality sort of commutes with our G-flow beyond one loop order. And this was a big confusion, some very confusing papers from like 20, 25 years ago, where people ran into exactly this issue. They found that it seemed like non-abelian duality screws up renormalizability. And it seemed that the theories can't be equivalent because one is renormalizable at two loops and one isn't. But in fact, say in this lowest dimensional 2D target space example and the 3D one, we know that if you supplement the non-abelian dual model with some particular alpha prime correction, then it will be two-loop renormalizable, and it will have the same beta functions as the original model. But I have some open questions. So we still don't know what is the structure of these counterterms after you integrate out A. So we want to understand what is their general structure in the physical target space. You know, how do you know which counterterms you need to add to get renormalizability? And a more general question is, if this is true, how is it that these hidden integrability charges are constraining the RG flow? We haven't really touched in integrability at all here. Is there a theorem? Can we try to make some general statement? I'll skip these 2 points and I'll just say, lastly, a comment about the converse statement. So you might try to imagine that it could be both ways. So maybe renormalizability is enough to get an integrable theory. That would be amazing, right? You can find integrable theories just by being renormalizable. But this is certainly not true, because Schwarzschild is a counterexample. So Schwarzschild is one loop conformal, which means renormalizable, because nothing runs. But strings on Schwarzschild are not integrable. So you would need some extra condition on the left-hand side. Renormalizability plus what? Plus something. So I don't know, what is that something? Yeah, so I'll stop here, and thanks for your attention.
We have time for more questions, but first let's thank now.
Yeah, let's unmute all and thank Nat.
Sorry for running quite late on time.
Yeah, you are quite actually fast to be honest. Any questions?
May I ask a question?
Yes.
Yeah.
Volodya disappeared.
I see. I pressed the wrong button. Sorry. Are those models Lorentz invariant? Because I remember eta deformed are not Lorentz invariant.
No, they're Lorentz invariant.
They're Lorentz invariant. Everything is okay. And then the question is, if you go to the large n limit, how to keep it non-trivial? I mean, all these extra terms, should you send also the level to infinity? Will you get a new parameter this way? Continuous parameter?
That's an interesting question. Large n limit. Yeah, I don't know what to say about that. So what exactly do you have in mind?
Oh, the principal chiral field, which is one of, the simplest representative of this family, yes, has a nice large n limit. It would be nice to have some model, Lorentz invariant, and having extra parameters. Like you have this parameter in ABJM model, yes, in analogy with this, the level becomes a new parameter, a single one there.
So in principal chiral model case, there's nothing to say here, but the corrections vanish.
No, my question is not about this one.
Yeah, but so what is known about large n for these, say, eta deformations?
It does exist, I think.
I'm not expert on this.
Your triple G symmetric model, that's what I mean.
Oh, I don't know. That's an interesting question. I have to think about it.
Okay.
Yeah.
Why I'm interested in it, because recently we studied this large n limit in principal chiral field, and making some statements about double scaling limit. It would be great to find a model where we could check the universality of our statements, like to have extra deformation.
And we had the seminar in our series about this paper, Volodya.
When?
Before.
Before, yes, Zhenya.
It went online, yeah.
Yeah, I was not present, but you know why I'm interested in this question.
Yeah, it's an interesting question. I think it's not clear.
Okay.
Okay, any more questions? No, doesn't seem so. So let's thank the speaker, Nat, again. And so let's meet next week, hopefully. So Andrea, could you comment? Yeah, let's thank you. Andrea, could you tell us about the next week's speaker, please? Very excited.
Oh yeah, we'll have Fyodor, and we asked him to do a review about the quantum spectral curve. And there were some requests to have one session about this. Maybe Fyodor, do you want to say something about what you will discuss?
Yeah, well, I will give just a pedagogical, hopefully, review of the quantum spectral curve, which is an integrability construction that captures exact spectrum of n=4 super Young fields. And recently, we also starts to acquire some applications for correlators.
All right, so thanks everyone for joining us, and see you next week. Bye.
Thank you.
Bye.
Bye. Bye.